aldehyde are very important intermediates during the oxidation of alcohols. We looked at the kinetic of oxidation of the corresponding aldehydes, and we compare on this figure the reactivity of the different fuels. Propanal, which is a 3-carbon aldehyde, is reacting slightly in the cool flame regime here, as you can see. And then there is the negative temperature coefficient, and then transition to high temperature. For butanol, you see the very strong cool flame and the small negative temperature coefficient here, transition to high temperature. And for pentanol, we oxidized it under less concentrated conditions, and we can see that we have a real very, very strong cool flame here and a small negative temperature coefficient. And finally, we oxidize isobutanol, and we can see that we have very little reactivity at low temperature, and this is due to the branch structure of the fuel here. So below 800 Kelvin, we have H-atom abstraction on the functional H-atom here, producing this RCO radical. And very quickly, the bond between the carbon chain and CO is broken, and we have the formation of CO plus a radical. And this is a fast process. It's much faster than the one we could get from a fuel to produce this R radical. So here, if we start with 4 carbon, this radical has only 3 carbon. So here we start with propane, 3 carbon, let's say. You get propyl radical. And it is well known that it's difficult to observe a cool flame from this radical when we oxidize directly propane. But if we start with butanol, we are able to observe this chemistry, this peroxidation, because there is a fast production of the alkyl radical here. And this is illustrated here. So we start with the aldehyde, you abstract this H atom here, you get this radical, and very rapidly you can either split this radical and release CO and the R radical, or you can also peroxidize this radical and produce different RO2 radical, which either react with themselves or react with HO2 or isomerize and then continue to peroxidize and after H-atom transfer, and you can get decomposition producing 2 OH radicals. So this is similar to what is observed with hydrocarbon. But in fact, chemistry is much more complicated than that. And this is what we can see on this figure here. Okay, so for some reason it was not showing full screen. This is what we can see on these figures. These are results that we obtained a few years ago in collaboration with people from the Berkeley National Lab and other places. And we could see that, in fact, this process of addition of molecular oxygen, H-atom transfer, again, oxygen addition, H-atom transfer, oxygen addition, etc., can go very far. But because the mass spectrometer we were using was not very efficient, we couldn't see more than 3 or 4 O2 addition. With the technique that we are using here in Orléans, we can go much further, and this is an example of a study concerning limonene, which is a terpene, C10 terpene. And here we have in blue the chemistry, which is normally only considered in atmospheric chemistry. So you start to oxidize that hydrocarbon. You get a radical, which is peroxidized, and then two of these radicals can react together, form this intermediate that decomposes, raising O2 and two alkoxy radicals. So these alkoxy radicals can also isomerize by H atom transfer from the carbon skeleton and produce this hydroxy radical, which can in turn peroxidize and continue with H chief, O2 addition, etc. And you can get very highly oxidized species here with 10 oxygen atoms. So this chemistry usually is ignored in combustion, whereas this one is considered, but only up to maximum the third O2 addition. So what we could observe under our experimental conditions here is that both mechanisms occur and that you are observing the formation of very highly oxidized products. And so these experiments were initially performed in a jet stirred reactor, and we continued with other systems. We used a motored engine, and by decreasing the pressure before ignition, we could probe the chemicals which are exiting the engine by simply bubbling also in acetonitrate. And I will show you some example of the species that we could observe in different systems. So the first are ketohydroperoxide. So those are formed after the peroxidation of the first radical to produce RO2, H atom transfer, and then second O2 addition and decomposition after H atom transfer, and you get this ketohydroperoxide. So the experiments were performed with a mixture of isooctane and N-heptane, 50-50, and we did some liquid chromatography analysis, and we follow the ions characteristic of this ketohydroperoxide, either coming from N-heptane or from isooctane. And we can see that there is a rather good match between the different chromatogram that we observed here, although all the peaks do not appear in every condition. So this indicates that the chemistry is following the same pathways, whatever you consider, if it's a reactor, laboratory reactor, if it's a rapid compression machine, or if it's an engine. And these are the second type of chemicals that we probe, keto dihydroperoxide. So it's one addition further of molecular oxygen. And again, you can see here that the trends that we observed, all these chromatogram are rather similar, whatever you consider engine exhaust or jet stirred reactor. And we plot here the variation of the signal as a function of temperature. And what we can see is that it's peaking around 600 Kelvin, which is below the maximum of the cool flame, which occurs around 640, 650 Kelvin. We did the same for diketo hydroperoxides, and although the signal is less, there are also similarities that appear, especially here for the C8 isomers. And again, the signal is peaking around 600 Kelvin. So, as I said, there are technologies which could be used to solve some of the problems. associated with fuel consumption or emissions, but also chemical kinetics can help solving technological problems. And I want to show you an example with HCCI experiments, ignition experiments. So HCCI is considered to be one solution for the reduction of both NOx, particulates, unburnt hydrocarbon, and CO emissions. So we ran some experiments a few years ago with an engine running under HCCI conditions, and we feed the engines with ozone. So we produce ozone with this device here, send ozone to the plenum, where we have both air and fuel. And we have this homogeneous mixture which is formed there, and here we can control the concentration of ozone that we are sending to the engine. And briefly, what we can see here, these are results obtained with isooctane. You can see that when there is no ozone introduced, there is almost no cool flame, no heat release in this region. And when we start to introduce ozone 10 ppm, we can see this cool flame which occurs here with 40 ppm. It's even stronger. So what's going on with ozone? Without ozone, the fuel has no other option than reacting with molecular oxygen. And this is a slow process, producing HO2, which can attack the fuel and produce H2O2. Then we can have decomposition of H2O2 to produce OH and speed up the oxidation. But overall, this is a slow process compared to what happens when we consider when we introduce some ozone. Because ozone will, when it enters the engine, it will decompose, produce an oxygen atom, which reacts readily with the fuel, produce an OH radical, which is very reactive species, which also attack the fuel and produce another radical here. So it's a fast process. So that explains what we observed here. And these are examples of the impact of increasing the ozone concentration on ignition. Here we recorded the in-cylinder pressure as a function of Crank angle. We did similar experiments with other oxidizers, NO and NO2, and what we could observe is that the effect of ozone is much higher than that of NO, which is higher than that of NO2. And this can be seen on this plot when we plot the impact of introducing these chemicals in the engine. So as a function of initial concentration of these three oxidants, and we can see that NO2 has a slight effect on ignition, NO has a stronger effect, and ozone has a huge effect. And to explain that, chemistry can help. As I said, with ozone, you are producing O atoms which attack the fuel and produce another very reactive species, OH, which will attack the fuel also. And then the process overall is very fast. With NO, the formation of OH, which is an important radical to consume the fuel, is produced through the reaction with HO2. And HO2 is formed slowly by interaction of the fuel with molecular oxygen. So even if the second reaction is fast, because the first reaction is slow, then it's less efficient to increase the reactivity of the fuel in the engine. And finally, nitrogen dioxide is less efficient because it first reacts with methyl radical to produce NO, and NO can react with HO2 to produce OH here, but NO2 also reacts with HO2 to produce HONO, which is not immediately decomposed, and when it decomposes, it produces OH radical. So overall, this process is is longer and slower, which explain the less important effect on ignitions. We did similar things with methanol, with ethanol and butanol, and we got very similar response. And so I will summarize what I presented so far. So detailed chemical kinetic models are needed for detailed chemical kinetic model need input